Hi everyone, and welcome to this week's programming tutorial video. We are going to learn how to train AI models for sea ice and leads classification. Sea ice plays a crucial role in the Earth's climate system, influencing ocean circulation and global temperatures. Leads, which are features in sea ice, serve as important indicators of climate change and influence heat exchange between the ocean and the atmosphere. The classification of sea ice and leads is essential for climate modelling, navigation, and environmental modelling. Sentinel-3, a European Space Agency satellite, is equipped with multiple instruments, including the OLCI and the SLS-TR. These instruments capture high-resolution optical and thermal data, which are essential for sea ice and lead detection. By using these datasets, we can train AI models to classify sea ice features efficiently. Our objective is to classify sea ice and leads using satellite images. To accomplish this, we will use a Google Colab-based Python script that applies machine learning techniques for image classification. The script can be accessed from our shared Google Drive repository where all the necessary data is located. First of all, we will need to connect our Google Drive repository to the Google Colab. To do this, follow the steps shown on the screen and remember to log into your Google account at the end of this step. Now that our Google Drive is connected, we can run our first few code cells that will load the data format and the necessary packages. We will then load the satellite image by defining the directory path in this section shown by the red box. Make sure to change this to your own directory path. Once the image is loaded, we need to make sure that our parameters match the area of the mask that we will be using. We can now read the mask file and print the corresponding images from the satellite and the image of our mask. Now we will use the next two code cells to create training data for our model. This is done by using padding to convert the data into arrays and will take into consideration the pixels on the edge. This data must also be saved before moving on to the next section of this tutorial. Once again, we need to connect our Google Drive to the Google Colab. Then we will run the code cells to connect our data directory and load our training and test data. Remember to change these paths for your directory. Using TensorFlow Python package, we will run and train a CNN AI model. Convolutional neural networks are widely used for image classification tasks due to their ability to automatically detect spatial hierarchies in images. The architecture consists of multiple convolutional layers that extract features such as edges, textures, and patterns, followed by pooling layers that reduce dimensionality. Fully connected layers then classify the images based on extracted features. Running this code cell will produce accuracy and loss curves for our models. Accuracy and loss curves help us monitor overfitting and convergence. Accuracy curve plots show how the model's accuracy changes over training epochs. A well-performing model will exhibit a steady increase in accuracy until it plateaus. Loss curves track the error in predictions over time. The loss function measures how far predicted values deviate from actual values. A well-trained model should show a decreasing loss over epochs. Running the next code cell will produce a confusion matrix. These matrices provide a breakdown of correct and incorrect classifications by category. They help identify misclassification patterns and allow us to fine-tune the model to improve specific weaknesses. In this example, most of the true labels are identified as the predicted labels, suggesting a good model. These code cells can be run using the scikit-learn Python package to produce a decision tree model and its corresponding confusion matrix. This is a combined learning method that builds multiple decision trees and merges their outputs to enhance predictive accuracy and reduce overfitting. Each tree is trained on a random subset of the data, and the final classification is determined by majority voting among the trees. Random forests are particularly effective when working with mixed numerical and categorical data, making them a strong baseline model. Finally, we will run the last few code cells to create a vision transformer model. Unlike CNNs, which rely on local feature extraction, VITs process entire images by dividing them into smaller patches and applying self-attention mechanisms to identify patterns across the entire image. This allows the model to capture long-range dependencies and structural information. VITs have demonstrated state-of-the-art performance in many image recognition tasks, making them a promising approach to sea ice classification. Always remember to save your models and load them to ensure they are functioning as intended. By integrating AI techniques with satellite imagery, this project aims to enhance the accuracy and efficiency of sea ice monitoring, contributing to better climate analysis and environmental decision making.